So this lecture would be not really following any straight path through my PhD candidature, but I will touch on a few of the things I've been working on and give a bit of a context to it, hopefully. And I would like to start acknowledging, and with the biggest gratitude ever, my supervisors for my PhD project, Professor Anja Redding, who is here today, and Professor Joe Whittaker and Associate Professor Jacqueline Halpin. So, this is the front page of my PhD thesis that I submitted a few years ago. And those of you with an interest in history in physics and mathematics might recognize that this is a document that's been typesetted in the LaTeX computational language. It's a computational mathematical language where we define the graphics of a document to communicate with human readers. So we wrap whatever we want to write, the most complex things that humans are interacting with, the beauty of the nature and our planet, the poetry of mathematics and logic, human interactions, feelings, memories and relations, all wrapped up into a computational language. And I'll give you some example of how the code might look like. So this is from the most important section of the PhD thesis, which is apparently the dedication. The first line defines that we start a new page in the PDF file that we generate. We give it some space to put the text on the center of the page, and then the dedication in loving memory of my mother. And then clear page, so we can move on to the scientific content. So I've been very fortunate. I have a loving and caring mother and father. My father is still around, thankfully.
Could you go a bit louder?
Yes, of course, sorry.
Yeah, we can't hear up the back.
That brought me up in rural Sweden and brought all the love and magic you could wish for as a kid. This is one of the last photos of my mother, here together with my niece, Marianne. And she loved spending time with the grandchildren. And in this photo you can't even see like the pain and suffering she went through in the last year. My mother was always very supportive of all my ideas and interests, but somehow me studying geology and geophysics was not really what she would care most about. All those dead rocks and computers, why don't you study and learn about people, society, art? Change the world and give children hope and a better future. Who knows, you might get kids one day and then you, well, whatever. It was usually quite a long pause. So, which is your favorite stone? So, in some kind of counterfactual alternative reality, I would like to imagine that there might be occasions where people are no longer along us can sort of tune in and observe what we're doing on Earth today. And me giving a presentation for the Royal Society of Tasmania would certainly be such an occasion where my mom would certainly tune in and check out what I'm doing. So hence I would like to give today's presentation also addressing some of my mother's concern directed to her. This is my childhood, somehow. It's an illustration from the illustrator and artist John Bauer showing a troll in deep conversation with a boy. However, I would like to focus your attention to the background of the photo, not the photo, of the drawing, of the painting. We see this big pile of huge rocks piled on top of each other, in a way that is quite rare to see in this part of the world. You might still see big boulders tumbling down Mount Wellington, Dolerite, that's sort of shaping the structure of the slope here. But those big kind of erratics is something that we associate with extensive glaciation. The Swedish word for those kind of rocks are jättekast, which means thrown by a giant. And they are all around the landscape where I go up. And you might ask yourself, what kind of giant would have thrown those rocks? Well, this is the giant. This is the Vexillian ice sheet that covered most of North Europe in the last glaciation. This map is a reconstruction for how the ice sheet would have looked like 15,000 years ago, when the ice sheet was already retrieving and was much bigger, more than 3 times bigger on its maximum extent. But at the time when people were living and hunting here in Tasmania, my hometown was still under 2 kilometers, 2.5 kilometers of ice. It's fairly recent in history. And this is actually one of the very few photos we have from 15,000 years ago in Sweden. It shows the Laxidian ice sheets in the background and all the rocks piled up. They've been dumped by the fast-moving ice sheet and left before any vegetation or any animals were living in the country. I need to follow my notes, sorry. So, when the ice sheet in Northern Europe disappeared, together with the ice sheet in Northern America, the Laurentian ice sheet, together with a much bigger Greenlandic ice sheet and ice caps even here in Tasmania, where did all the water go? Well, it went into the oceans, of course. This is how Tasmania and Southern Australia would look like during a time of glaciation. The coastline being far away from the present-day coast. You could easily walk from the mainland to Tasmania, you could live, you could hunt for many, many generations in what is now the ocean. I tend to sometimes think about and give some kind of a respect for the real estate people back then, selling very expensive coastal properties for very high prices, and then seeing the properties being flooded underwater and disappearing. No, of course it didn't. But this is where the water went to form the world that we have today. So the global sea level rises to about 100 to 120 meters due to the big ice sheets in Northern Europe and Northern America particularly. After my childhood in rural Sweden, I moved around a bit. First in northern Sweden, actually at the same latitude as Casey Station in Antarctica, but just in the north. Then I spent some years wandering around in Russia and West Africa before I finally settled in Copenhagen to eventually study geology. It took a while. Denmark is very flat. It's the landscape is quite, compared to Tasmania, it's not very inspiring, to be honest. The highest mountain in Denmark is Møllehøj, which is 171 meters. It's about half of Mount Nelson. And I've sometimes started to think that if the global sea level rise since the last glacial maximum had just been a few % more, then Denmark would just be like a German archipelago with some nudist beaches and ice cream stores. So we have to be very grateful for that it sort of stopped where it did stop and we didn't melt more of the Antarctic ice sheet back then. However, the Danish underground is the more interesting. Even if it's a small country, it's smaller than Tasmania, but it's exists on top of a very deep sedimentary basin. This map shows the depth in meters down to the base of the Sechstein Formation, which is a formation of evaporites, salts, gypsum that was formed during Pangea time, when the shallow ocean was bringing water over the continent that was evaporating, leaving behind a brine that was eventually forming salt crystals and rock units that formed thick, hundreds of meters of thick salt structures. Since that was the onset of the Mesozoic, more sediments have been added, more siliciclastic and carbonate sediments have been added on top. So in some places we have over 10 kilometers of sediments. And I did my undergrad studies and my master's thesis. I was very interested in those kind of structures, particularly how the salt was moving and deforming the carbonates on top of it. So what happens is that salt is actually not very dense compared to other rocks. So when you have salt, halite or gypsum, under 10 kilometers of rocks, it's tried to sort of find a way to get out of that sort of uncomfortable high pressure on it. Similar to if you imagine like pushing a birthday cake from the top, the cream will eventually sort of find a way up through the sand cake. And that's what we see in Denmark as well, that the salt structures have been pushed up through the stratigraphy up to the surface. And that caused a lot of interesting aspects for oil and gas. And I wanted to work in oil and gas. I was learning reflection seismology, how to understand where the oil plays are how to get really rich really quick. And that salt structure, the sextine formation, was very important because that forms a cap rock. Oil and gas are trapped under it. You can't penetrate through it. So if you drill on top of the sextine in a good location, you can get a very good oil play that makes you rich. However, I should also mention that my main interest was the carbonates about that are formed from ocean-living creatures, coccolithophores and bivalves or whatever organisms that build shells to protect themselves against predators. They were over millions of years and billions of numbers. They were forming huge geological units, the big chalk of Denmark, during a time that we called Danian or Zealandian in geology. Zealandian after the Danish island, Zealand. Denmark is not the only place that is close to the sea. This is a photo from the Charles in Brahmaputra in northern Bangladesh, near a town called Rangpur, where the Brahmaputra River every year deposits sediments. Every year in the monsoon season, the Charles, the islands are changing due to the flow of the river. This land is very, very fertile. But if you're living there, you can't plan ahead because next season the landscape might change. You need to go in different locations. Actually, according to some resources that I found, 150 million people globally lives within 1 meter above the sea surface today. And many of them are very vulnerable. Because when the sea level is changing, it doesn't happen millimeter by millimeter over many, many years. It happens in terrible nights with storms and panic and chaos when the storms are hitting the coast. This photo is from the town Kita. It means the head of sand in eastern Ghana, where people are reading the Bible a lot, and they're very familiar with all the aspects of the theology. And they all know very well that they should not build their houses on sand. But what can you do when that's where the Europeans decided to build a trading fortress? That's where you can make your outcome. And the sea is full of fish. Used to be full of fish. Now it's not very full of fish anymore because industrial fishing takes place off the coast. So now Ghana actually have to import food from Asia to survive. So where is that water that I'm talking about that could potentially threat the beautiful architecture of Copenhagen and the fertile land of Bangladesh, as well as the coast in Ghana? Well, here is that water. This might actually be on a flight where Koti, who is in the audience today, was with me, flying over the Denman Glacier in East Antarctica. Denman Glacier is a big glacier, but it's not the biggest by far. But it still holds enough water for a global sea level equivalent of 1.5 meters. So if that glacier would go, well, the Charles would be gone and Copenhagen would be gone. Antarctica is big. It's huge, much bigger than Australia. But it's very high, very elevated. The ice sheet builds up many thousands meters over sea level. So even if a small region of the continent is changing, as we see right now in West Antarctica, that has a big global impact. This is one way to look at Antarctica, and this illustration is quite deceiving because the vertical axis has been accelerated, I believe, maybe 5,000 times. But it hopefully gives some kind of impression of how the ice sheet looks like and how it will interact with the oceans. The snow is accumulating on top of Antarctica over millions of years. Starting from the elevated mountainous regions, ice caps have been growing and eventually forming a big ice sheet. And thanks to its gravity, again, like sort of think about like a layer cake or a pavlova with poorly whipped cream, it's sort of flowing towards the edges. This will happen to Antarctica too. Eventually the ice is shaping into fast-flowing glaciers that reach the oceans, where it melts due to glacial melting or calving of icebergs or even surface melting. Somehow Antarctica looks like a big ball that sort of holds the ice sheet within it. And I will talk a little bit about why that could be. The solid earth beneath the ice sheet are interacting with the ice sheet in many different ways. Or not that many, three ways. One way we already talked about, the erosion and sedimentation, that the ice sheet and the glaciers are taking the rocks, scraping, forming the landscape, moving the sediments from one place to another, placing different giants thrown around Sweden, creating big sedimentary basins next to the glaciated continents. Another aspect that we'll talk about next is the glacial isostatic adjustment. If you think about the deep, thick ice sheet, many 1,000 meters thick, it will add a lot of pressure onto the crust, onto the lithosphere, and push it into the mantle of the Earth, which is more plastic. And eventually I will get a bit to geothermal heat as well. It's been maybe my main interest. So glacial isostatic adjustment. It's been known for a long time, even though people didn't know why it happened. So again, I'm back in Sweden, where people have been noting that the land seems to be rising from the sea, or maybe the sea was disappearing over time. Places where the Vikings used to sail are now dry land, and some places are named as being an island, but it's now a hill. And the scientist Celsius, that gave name to our temperature scale a while ago, he was aware of this, and he put a mark on the rock, saying like, well, here's the sea level right now, let's see how it changes in the future. The measurement was repeated 100 years later, then again 200 years later, and we can see how the land is uplifting from the oceans, from the sea. However, I should mention that the uplift is now decreasing, or the sea level rise is now slowing down, and that's not due to the changes in the way that the continent is responding to the glaciations, but it's because now the local uplift is competing with the global sea level rise. So we see a slowing down in how quickly the land is rising. In some parts of Sweden, as in particularly in the north, you have an uplift of maybe a meter a century. So it's a quite big concern for people like mapping sea charts, for example, or infrastructure in general. So how would Antarctica look like? The map to the left shows how Antarctica would look like today if you, by some kind of magic, would suddenly just remove all the ice and leave the subglacial topography as it is. So big parts of Antarctica is under sea level, big subglacial basins with shallow ocean, if you like, if you remove the ice, but also some deeper troughs, deeper spots where the glaciers have been eroding down deep into the crust. If we remove the ice and then we leave Antarctica there untouched for a long time, many hundreds of thousands of years, it will look something like the figure to the right, where the crust is completely isostatically relaxed and the shallow oceans have been removed by the uplift. And this is actually a good thing. It helps us stabilizing the ice sheet. If the oceans are warming and the edge of the ice sheet is melting, well, an uplift of the continents actually helps us to stabilize it to, if you like, move it away from the warming oceans. The question is, at what rate is this happening? And that's the $1 million question. If you imagine a weak Earth, and that's a lithosphere that is hot and thin and warm, and it can easily respond to the changes in the ice load. But an old and cold and thick lithosphere responds much slower, just like my email replies. So we need to understand the geology, we need to understand what kind of tectonic settings you have under the ice sheet. And people don't agree on that at all. Different studies have, using different methods, different approaches, have been suggesting different kind of origins, different kind of sedimentary basins. Some people use the geological observations from the coast and from the outcrops and extrapolated from that. Other people used geophysical data only and used that to understand the tectonic setting of the continent. I won't go to any details here, but I just want to show the disagreement between previous studies. You can think about this kind of deterministic mapping as mapping out polygons with really sharp boundaries. Here the geology is something. You move 1 meter to the side and the geology is something different. Sometimes you can have a boundary that defines the geology, even though the properties of the landscape, if you like, are the same, but they might have different origins. And sometimes you might have a polygon that defines a geological region or terrain, if you like, with a certain set of properties, but you can only define it by boundaries. I started to think about it more as gradual changes in the geological setting, not only because of the geological history itself, but also limited by our measurements. Where would you move out from a cratonic setting and into a mobile belt? How does it look in the landscape, in the subglacial landscape that you can't see? How would it look like in the geophysical data? Or maybe we should even imagining a case where we know that there is a sharp boundary somewhere, but we can't detect it because it's, well, like in William Turner's painting, it's hidden behind the storm, but there is a boundary somewhere between the sea and the sky. I'll leave you with that until I find my notes. So inspired by that, I tried to map the geological boundaries of the continent by using the limited geophysical data we had, and carefully acknowledging the limited precision and accuracy of the datasets. So sometimes, in the case of picking boundaries from the seismic tomography, we cannot be very precise because the seismic tomography itself has a resolution of hundreds of kilometers. And in some cases, I cannot be really sure that it was actually a boundary. But then by applying some computational and mathematical voodoo to it, and the voodoo in this case is some very fundamental set theory that you will learn in high school, we managed to combine the different detected boundaries from different geophysical datasets and combine them into one model of the boundaries in Antarctica as a first approach to robustly map the tectonic setting of the continent. We also tried it for Australia, where we know the geology much better, and our findings agreed fairly well with the known geology as it's been mapped on the surface. That we could detect some aspects of the boundaries, but of course the problem was that how can we actually interpret and use this data when we don't know the properties of the crust? Sort of following my PhD project, the next thing I would like to talk about is geothermal heat. Earth is hit by radiation from the sun of a short wavelength and very organized, and then it heats up the planet. It's the engine behind all life, the photosynthesis, and the storms and the ocean currents, and then eventually it's radiated out into space again as low wavelength radiation. However, the interior of the Earth is quite warm, and that's been known for a long time. People have been observing geothermal springs or volcanoes, and this painting showing the capital of the underworld from Paradise Lost shows that we were really aware that it's hotter under the surface. And now we know more, thanks to seismology particularly. We understand that, well, the temperature is increasing as you get into the inner core of the Earth. So the x-axis on this diagram to the left shows the temperature. It's higher in the inner core. As you get out to the outer core, some convection starts, and in the mantle, further heat is moved up to the surface, cooling down the lower mantle, and then the lithosphere sort of forms a lid over the Earth that traps the heat. And we can map how much heat is leaving the Earth and going into the surface. And the unit we are using for a map like this is in milliwatts per square meters. Milliwatts per square meters, that's very, very little. Compared to the energy that we reach by the sun, it's only a tiny fraction. And to get some kind of understanding about the meaning of milliwatts per square meters, or if this slide didn't turn out very well, we can use the humble Kmart tea kettle. It's usually about 1 kilowatts of power. If you imagine one of those kettles inside the solid Earth, heating the crust for millions and millions of years continuously, in some regions you have to separate those heat sources 180 meters or so. In other regions about 80 meters, continuously producing heat. And that's what we're trying to map out. So why are we interested in mapping out that in an Antarctic setting? Well, that's because the solid Earth interacts with ice sheets. There are many aspects of the geothermal heat that are very shallow. formed by the subglacial landscapes, while other components are formed deep inside the Earth. There's even some, well, not some, it's quite a big part, like maybe a third of the total geothermal heat of the Earth is still leftover primordial heat from when the Earth was formed by rocks and gases banging together to form the planet. Similar to how the blacksmith can heat up a piece of iron by hammering it, the Earth was formed as a melted blob of iron and silicates, whilst it was eventually started to cool down the surface. Lord Kelvin, he used that kind of cooling rate to actually estimate the age of the Earth, and he concluded that the Earth is probably about 100 million years old, at least not more than 200 million years, from the cooling gradient. However, what Lord Kelvin didn't know was about radioactive, radiogenic heat. Most of the heat, maybe 2/3, is formed by the radioactive decay of uranium and potassium and thorium inside the Earth, particularly in the crust. And that's where things start to get interesting, because the crust is where the geological processes are changing the landscape all the time. So there's a big variability of how much heat is actually formed inside the Earth. We care about it in an Antarctic setting because the surface of the ice sheet is typically fairly cold. The shallow part of the ice sheet had the temperature that the atmosphere had. So if you're coastal, it might be -20 or -30 degrees. But when you get down to the base, you quite often get close to the melting point, the pressure melting point. Even in the very cold interior, as the plot to the left, where the surface temperature is maybe -60, once you're at the base of the ice sheet, you're close to the melting. So just a little bit of heat from those tea kettles that are added at the base of the ice sheet have a big impact on the temperature gradient of the ice sheet. And to prove that, we made an experiment using Whittaker's white chocolate. So you have a piece of chocolate put on a sloping heat plate. As we're heating it up, the base of the ice sheet, or chocolate if you like, start melting and reduces the friction towards the subglacial landscape by melting. And eventually that had the possibility of speeding up the dynamics of the ice sheet until it eventually collapses. So how can we map the geothermal heat in the interior? There's been quite a few different approaches to do that. And I would try to avoid today to go into the technical details about modeling geothermal heat. But I decided to go for an approach that I would call similarity approach, where we're looking for similarities. And similarities doesn't mean that it is the same, but we are using geophysical data to map out which part of Antarctica is similar to other continents to understand better. This is the equations we're using to do so. And for those of you who like equations, you see that it's very simple. It's a normal distribution. We are adding all the similarities together, and then we're putting it into a kind of a power function to enhance locations where it is similar. It can look like something like this. Here we have a point in East Antarctica, and we look at the rest of the world. Where do we have something similar to that from a geological and geophysical perspective? It turns out that this particular location in East Antarctica looks to be similar to the flank of the Amazon Craton and the Congo Craton, maybe some similarities to the Slave Craton in northern Canada. We don't know anything more about it. We don't know really the history of this point, but we know that it's similar to those locations. We could also take another location in West Antarctica that appears to be most similar to eastern China, Vietnam, or maybe the Macquarie Ridge. This forms a very different tectonic setting. Again, we don't know exactly what the tectonic and geological setting of this location in West Antarctica is, but we know that it's most similar to those places. Doing so, we could use measurements of geothermal heat in other continents and put it back onto Antarctica using the similarity approach. And we produced I would say, fairly robust estimate of the subglacial geothermal heat. So it can provide it to ice sheet modelers and glaciologists that want to understand the thermal content of the ice sheet and the glaciers. The problem is that we still don't really understand, or until we worked on it, we didn't understand the uncertainties involved. And one way to understand uncertainty when it comes to to map similarities is to go to information theory and learn from signal processing and information entropy. The entropy of an information system can range from very low entropy. If the entropy is 0, there's no discussion. We have only one solution. There is no potential other interpretations. And when the information entropy is at its maximum, we are dealing with complete noise. We don't know. There's no information in it. We can't differentiate anything useful from it. It's only noise. But it's a bit of a sweet spot in between, where we still know fairly well what's going on, but we allow ourselves to have some degrees of freedom to interpret the system. And we did map Antarctica using information entropy to map out where we understood the geology well and where we didn't understand it at all. And unfortunately, we didn't understand most of it very well at all. But the bluer, darker sections here, that's where we have a lot of noise. That locations can be interpreted in many different ways, but in some locations we can be fairly precise. This is the kind of geology we must have in this location. Developing this kind of theoretical framework can be brought forward, not only to model geothermal heat, but also to model the geological setting or other properties of the lithosphere, and that's something that we're working on now. I'm sure I'm running a bit short of time, so I will go to a conclusion. So, dear Mum, this is how I wanted to explain my PhD project to you. Geology is about understanding the Earth and its inhabitants, the past and the future. Geophysics teach us about the time and space changes and hidden worlds. We need to understand the Earth to mitigate the suffering and to make better decisions in future. Mathematics is the language and poetry we're using. Computers can be very useful tools. However, they require some care when used. And thanks for asking, Mum. My favorite rock is Tillite, and I brought a piece of Tillite. Because that rock tells so many stories in one, so I'm happy to get back to that if I get any questions on it. And here is your grandchildren. Thank you very much.